Hello everyone, we are studying the surface chemistry chapter from the paper first of S.Y.B.Sc. In this chapter we have studied the introductory part of the adsorption phenomenon, types of the adsorption, and now we are studying the different theories of the adsorption. So first theory we have studied in the last lecture, it is Friendlich adsorption. And in that we have considered how the gas molecule will get adsorbed on the solid surface, and secondly we have also studied in case of the solution how the adsorption process occurs. So solute and solutions, solute is act as the adsorbate material for the solutions. So next theory we are going to study in this lecture, it is the Langmur adsorption. So the scientist Irving Langmur in 1916 he has studied the different cases for the adsorption process, and depending upon that he had given the assumptions for this theory. So we know that the adsorbate molecule, so when we consider the gas molecule at the adsorbate, it will get adsorbed on the surface area of the adsorbent material. So in these assumptions he has said that there are different spaces which are present on the surface area of the adsorbent material, and these are the active spaces for the adsorption. These are called as the elementary spaces. So number of the elementary spaces are present on the surface of the adsorbent material. So when gas molecule it will having the same affinity, this spaces having the same affinity for the gas molecule, and it does not affect the neighboring surface area or the neighboring elementary spaces for the adsorption property. Now when gas molecules will get adsorbed in these elementary spaces, so in that case the unimolecular uniform layer of the molecule it is formed on the solid surface. So unimolecular layer is formed according to this theory. Multimolecular layer it is not given or it is not found to be possible, because as the distance increases the intermolecular forces will fall off rapidly. So he had considered only unimolecular layer of the molecules, it is formed in this adsorption process. Now in this case he has studied that two processes namely occurs on the during adsorption process. So first step or the first stage is the adsorption of the molecule or condensation of the gas molecule on the surface area of the adsorbent material. In the first step what happens, the gas molecules will get condensed and get attached themselves on the elementary spaces, and these elementary spaces when gas molecule it is attached or it is adsorbed, it does not affect the affinity of the adjacent elementary space. Again this second process is the desorption process. In this process the gas molecules which are adsorbed on the surface, they will undergo the forces, will get break, and molecules will get removed away from the surface. It is called as the evaporation or the desorption of the molecules. So this process exists in equilibrium with each other. So when equilibrium is reached, some constant amount of the adsorbate material it get adsorbed on the surface of the adsorbent. So these two processes are always happening during the process of adsorption. First is the condensation of the gas molecules on the surface of the adsorbent, and second is the evaporation of the gas molecule, or it is called as the desorption process. Now let us consider the mathematical expression if we want. It is given by the Langmur scientist. So first he had assumed that the particular fraction theta of the molecule or the gas molecule will get occupied on the surface area, and the theta 1 minus theta is the unoccupied surface area for the adsorbent material. It is shown here. We can see here this square is given. In this square, the occupied fraction, if we assume that it is the theta, so this is the fraction shown here by the lines. So this part, it is the occupied fraction, it is called as the theta. So in the adsorption process, what happens? Some molecules will get attached themselves or get bind to the surface area in the particular time, and this fraction, it is called the theta. It is the occupied fraction theta. Now the remaining part, if we consider the in 1 square meter area, 1 square centimeter area, then the remaining is the unoccupied fraction, which is shown empty here. It is 1 minus theta because it is given for the 1 square centimeter. So unoccupied fraction becomes the 1 minus theta, and this overall surface area, we can consider this theta is the occupied fraction here. Now in this case, when we consider the adsorption process, adsorption on the adsorbent, we have considered the two processes. First is the condensation of the molecule to occupy some area on the adsorbent material, and second is the evaporation or desorption of the molecule. So these two processes always occur during the adsorption, and from these two processes we can calculate the particular expression. We can determine the amount of the adsorbate material which is occupied, that is theta. We can calculate the value of theta. So for this adsorption process, we can consider now adsorption on the adsorbent. It is given as the rate of the condensation. So how much molecule will get condensed on the surface area? So the rate of the condensation for the first step is found to be directly proportional to the pressure and the unoccupied space on the adsorbent material. So already we have studied that change generally in the adsorption process, we are keeping the temperature constant and we are changing the pressure. So for that, at the lower pressure, the adsorption, it is less. If we increase the pressure up to certain extent, the adsorption process goes on increasing, and at very high pressure, adsorption is found to be constant or it will never occur. So we can say from this, it is proportional to the rate of the condensation, that is rate of first step condensation. It found to be proportional to the pressure into the unoccupied area, that is 1 minus theta. So we can put the proportionality constant for this equation. So rate of condensation equals to K1 into P into 1 minus theta. So we can assign this equation as first. So this K1 is found to be the proportionality constant for this equation. Now again, from the kinetic theory of the gases, we can say that at the constant temperature, these gases will show the particular kinetic energy and they will show the particular rate of condensation and the evaporation. So this is depending upon the pressure. So from the rate of evaporation, if we consider the second stage, that is rate of evaporation, it is found to be directly proportional to the occupied area. So why we have considered that is theta? Because evaporation occurs only in that area where adsorption is already taken into consideration, or already adsorbed molecules are present in that area, which is the theta. So the evaporation is only dependent upon that particular fraction or the theta. So rate of the evaporation, it is proportional. We can write proportional to the theta. So we can put again proportionality constant. So the rate of the evaporation, we can write K2 theta, where K2 is the proportionality constant. Now in this case we know that in the first equation, so at equilibrium what happens, the rate of the condensation, it is equals to the rate of the evaporation. So this simultaneous process occurs. So at equilibrium these two processes are found to be equal. So we can write the equation. First it is given for the condensation, K1 P into 1 minus theta is equals to equation second, that is K2 theta. So these two are equal, that is rate of condensation is equals to rate of evaporation. So we can now rearrange this equation. We can write here K1P minus K1P theta. So we can multiply this 1 minus theta by K1P. We are getting this value. K1P minus K1P theta equals to K2 theta remains as it is. Now we can shift this minus K1P theta on the right hand side. It becomes plus K1P theta. So remaining is the K1P equals to, we are getting here, we are getting K2, we are getting K1P theta plus K2 theta. So K1P equals to K1P theta plus K2 theta. Now we can take the common theta here. So theta can be taken as the common. So what we are getting, theta into K1P plus K2. So we are getting this equation. Now this P, it is K1P, and this is the value which is present in the bracket. It is multiplied to the theta. So if we put this value or shift this value on the left side, so it becomes divided to the K1P. So what we are getting, theta equals to K1P divided by this value K1P plus K2. So we are getting the equation 3. So from this equation 3 we can calculate the value of theta, that is the fraction, which is fraction of the molecule which is the area, fraction of the area which is occupied by the gas molecule. So this is, we can calculate. So from the kinetic theory of gases and also Friendly's adsorption, we have know that the ratio of the molar mass of the adsorbate to unit mass of the adsorbent material, this ratio is found to be proportional to the occupied area, that is the theta. So we can again, from the kinetic theory of the gases, we can put this equation. We can write this equation, X upon M, that is the ratio of the molar mass of this adsorbate material with unit mass of the adsorbent material. This ratio is directly proportional to theta. So we can put the proportionality constant, X upon M equals to K theta. So this theta, which is the value of the theta, it is given in the equation 3. So we can put this value of the theta into this equation. We are getting X upon M equals to K into bracket K1P plus upon K1P plus K2. So now we can write this equation. We can multiply this K with this value. So we are getting K K1P upon K1P plus K2. So now we can rearrange this equation as K K1 divided by K2. If we separate this denominator K2, we can write K K1P divided by K2. So we have taken the K2 common for this and divided by K1 divided by K2. So we have divided both of the side by the K2 for this equation. We can divide it K K1P divided by K2 and K1P plus K2 divided by K2. So we have divided this both side by K2. We are getting this equation, and further we can rearrange this equation. We are getting the X upon M equals to K K1P divided by K2 into P divided by K1 divided by K2 into P plus 1. So this K, all these K's, K1, K2 and K, all these are the proportionality constant for the equation 1, 2 and 3. So all this constant we have separated and we can put the value here. We can write a, small a, for this K1 divided by K2. So we can put this value a, which is again constant, all these are constant, so we can put this value a for this constant, and we can, if we write b equals to K1 divided by K2, so this equation becomes x upon m AP divided by BP plus 1, where A is the K1 upon K2 and B is the K1 upon K2. So simply we have put the another constant, we have replaced the constant K1, K2 and K by the A and B. So we are getting this equation x upon m, which is equals to AP upon BP plus 1. So this is the final equation we have obtained for the Langmur adsorption. Now we can again study this adsorption by using the graphical method. We are always using the equation to plot the graph, and from this graph we can determine the value of the constant. So already we have studied this type of the graph for the friendly adsorption. Now let us see this equation. We can convert it into straight line equation. So we can write here P upon x upon m. So this equation, it is rearranged, which x upon m AP divided by BP plus 1. If we rearrange this equation, we are getting P upon x upon m. So only P is on the numerator side, so we have taken this P on the left side. We are getting P upon x upon m equals to B upon A into P plus 1 upon A. Now this equation, it is found to be similar to the equation of the straight line, which is y equals to mx plus c. So this equation is, we can using this equation we can plot the graph P upon x, P divided by x upon m versus P. So P is the pressure here. We can plot this graph, and from this graph we are getting the intercept value equals to 1 upon A, and if we draw the slope on the any point, at any point on this straight line, so we are getting the slope equals to B upon A, which is the value of this constant, proportionality constant. So the value of proportionality constant can be determined from the graphical method. We are getting the value of B divided by A, and again we are getting the value of 1 upon A, which is obtained from the intercept. So as this is straight line graph, we can determine the values of the constant. So this is about the Langmur adsorption isotherm. In the next lecture we will discuss the different types of the adsorption isotherm, isobar and BAT theory for the adsorption. Thank you.